Let's analyze the convergence of mirror descent algorithm, which I skipped last week. So this is Theorem 4.2 of Bubeck's textbook. So where this theorem told us what is the convergence speed when the rho function is rho strongly convex with respect to the original norm, and FB convex and ellipsis continuous with respect to original norm. And let R square is supremum of pi x minus pi 1. So the maximal difference between any point inside your constraint set and your starting point. So this was the original statement in the textbook, but I think the distance between any point in our constraint set and the Bregman derivatives and the starting point is more right expression, I think. So I think this should be Bregman divergence between x and x1 with respect to the pi function. Then mirror descent algorithm with this step size have this convergence rate. So this convergence speed is very similar with convergence speed of gradient descent algorithm when the objective function is ellipsis continuous. Right. So let's show this. So from the convexity of function f, we naturally have this inequality. And from the definition of mirror descent algorithm, the gradient appear when we update y as +1 from xs. We first map xs to the gradient space, the mirror space, gradient of pi xs, and then move the gradient as much as gamma minus gamma times gradient of fx. So this is equal to gradient of fx. And this comes from the simple equation. So this comes from the definition of Bregman divergence. And for this inequality, we use this property. So I just rewrite the definition of Bregman divergence of these two, and then rearrange them. And from the convexity of Bregman divergence itself is also a convex function, and every time we find the x s plus 1 as argument over your constraint set with respect to the objective function, the convex objective function, Bregman divergence between x and yt plus 1. So since xs plus 1 is the solution of a convex optimization problem, so from the definition of convex one very important property of convex optimization problem, for the solution we have this inequality. This is always less than or equal to 0. Okay, so that's why we can upper bound this previous term by this. I mean, the minus this term is always a negative. Okay. So therefore, when we define x bar as 1 over t from t equal to 1 to capital T fxt, xt, sorry. Then from the Jensen's inequality, we have this because f is convex function. And from the previous slide, we have this inequality. fxs minus fx star less than or equal to this, and we can decompose the sum of Bregman divergence into two parts. This term and this term is the first part, and this term and this term is the second part. Then the sum of the red part, the sum of this red part cancelled out by themselves, because this is Bregman divergence x star and xs minus x star and xs plus 1. So as you increase the index of s, then this will be gone by the next term of the first term. So in the end, we have this and the second term. Okay. So indeed, we can upper bound this term by gamma L square over 2 rho. So we can replace this term by gamma L square over 2 rho times capital T, because there are capital T term. And so we have this. And then when we replace gamma by the definition of gamma, finally we have this theorem. Okay, so in the next slide, I will show this inequality, why this is hold. So from the definition of Bregman divergence, we can rewrite a Bregman divergence between xs, ys plus 1 minus Bregman divergence between xs plus 1, ys plus 1 like this. And again, from the low strongly convex of your pi function, we have this. So which comes from the low strongly convex. And then from the definition of xs and ys plus 1, since ys plus 1 is the gradient of pi ys plus 1 is just update from gradient of pi xs as much as the gradient of fxs with step size gamma. We can replace this term by this. And ellipsis continuity make this inequality, so we can upper bound this term by this from the ellipsis. Okay, and then so we can upper bounding this term by this. Why? Because when we think this as an x value, then basically this is a quadratic function, gamma lx minus rho over 2 times x squared. So how can we optimize this with respect to x? So this is optimized when x is equal to gamma L over rho. Okay, so that is the result.